Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 31 of Algebraic Topology. In previous lecture we studied what are covering spaces, and in today's lecture we will first study what are group actions, and then we will use our discussion of covering spaces and group action to discover the relation between the covering spaces and the fundamental group. Okay, so practically speaking, this lecture is our last lecture of this course, because in the next course, in the next lecture, we are going to just review the whole course. So let us remind ourselves what is a covering space. A covering space of a space X is a space X tilde, okay, together with a continuous function satisfying the following conditions. Number one, this covering space X tilde should be path connected topological space, and the second condition is for every X there exists an open neighborhood U such that P inverse U is disjoint union of open sets such that the restriction of P on UI from UI to U is a homeomorphism. So in other words, what we are trying to say is that if there is an X, then there exists an open neighborhood of this X, and such that the inverse image of this U, so that is P inverse U, is disjoint union of open sets. Okay, so let me remind you again that we can say that P inverse X is a discrete set because P inverse U is going to be disjoint union of open sets. Okay, so we can say that the inverse image of this is U1, U2, and up to UM, and up to so on. Okay, so remember that X tilde is a path connected topological space, but in this depiction, we are seeing the things as sheets. Okay, so it is just a depiction, and in fact this X tilde is a path connected topological space. So in fact this is inverse image of U. Okay, so it's going to be disjoint union of open sets. Okay, so we denote the covering space by X tilde P, where P is the continuous function and X tilde is the total space or the above space, and X is called the base space. Okay, the map P is called the covering projection. Okay, and X tilde is the covering space. And then we discussed this theorem called the lifting lemma. So what is this lifting lemma? So let's read the statement. We have a covering space with this continuous function and the covering space X tilde, and there will be of course some base space X. Okay, if there is a path in the base space, okay, there is a path in the base space, and this path has starting point to be x naught, then this lifting lemma says that we can lift this path to the covering space. Okay, so once again I'm going to sketch the covering space to be a collection of sheets. Okay, so let's say this sheet is x1, this sheet is x2, and once again this X tilde is path connected. So but this is just a depiction, just to realize the fact that we can say roughly that the covering space is going to be some number of collections of this base space X. Okay, so it's a very rough statement. Okay, so now this lifting lemma says that if I have a path in the base space X, then there exists a path. Okay, so remember there are many sheets. So one sheet which resembles X, and another sheet which resembles X, and there will be many other sheets as well. So if I want to lift this path, then to which sheet should I lift this path? So the answer is provided by if X tilde naught is in the fiber of X naught. So what is the fiber of X naught? So the inverse image of X naught is going to be a collection of points of X naught. So for example X naught tilde. Okay, so let's call it X naught tilde, X1 tilde, up to so on. Okay, so in the second sheet there will be another point X 1 tilde and up to so on. So these are all in the fibers of x naught. So when I choose this x naught tilde, then basically I'm choosing the sheet. So I'm lifting, so I want to lift this path to this sheet. Okay, so in other words, we are saying that once I fixed the sheet, then there will be a unique. Okay, so remember there is this word unique. There exists a unique path inside the covering space, and there exists another condition which says that so if this is a path, then of course this means that there exists a continuous function from the closed interval 0 1 to this topological space X. And if we have okay, so once again we have this projection. Okay, and if we have a lift of this path, then if it is a path, then there will be a map from closed interval 0 1 to this covering space X tilde. Okay, and this result also says that if I move along F tilde and then move along P, then I will reach at the same path. Okay, so these are very, very strong conditions. So for example, this uniqueness, this condition, and we are lifting a path inside this, and this fixing this x naught tilde. Okay, so this is the lifting lemma, and then we had the discussion of this covering homotopy lemma. So this covering homotopy lemma, so I'm going to just use a rough statement. So this covering homotopy lemma says that if there are two paths which are homotopic to each other inside the base space X, then if X tilde is the covering space with the projection P, then there exists of course if there are two paths F and G, then we can lift them to paths F tilde and G tilde, and this covering homotopy lemma says that these two lifts will also be homotopic to each other. Okay, and then we had this theorem which says that if we have a covering space of X, then this map which is induced by the functor pi 1, which is we can just say that, so pi 1, remember pi 1 is a functor from the pointed topological spaces to the category of groups. Okay, so from the category of pointed topological spaces to the category of groups. So this functor will give me images of the maps. Okay, so we have a continuous map P from X tilde to X, and we have taken X naught tilde in the fiber of X. So in other words, we can say that when we apply P on X naught tilde, then I will get this X. Okay, so using this functor, I can get image of this continuous function, which will be a map from pi 1 X tilde X naught tilde to pi 1 X X. Okay, so this map between these groups, which we can also call P lower star, is guaranteed by our discussion of the functor pi 1. But then what is this theorem really about? So this theorem says that this is going to be an injection, and we proved this result, and the result was very simple, but the consequences of this result are very, very important. So in other words, we can say that given any covering space, I will be studying subgroups of the fundamental group. Okay, so covering spaces corresponds to subgroups of the fundamental group of the base space. So that is the important line. Let's begin with today's lecture. So as I said earlier, that we'll be defining a group action, and we will be using this group action to explore the relation between the covering spaces and the fundamental group. So let's see what is a group action. Okay, so in fact it's not one definition, there are two definitions. So one is for the sets and the second is for topological spaces. Okay, so let's first ignore the word topological space, and let's see what is this definition, and then we will see if it is if we replace the word set with topological space, then what's the definition going to be. Okay, so let G be a group and Y be a set. Okay, so we are not requiring anything else, just a set. Okay, so of course every group is a set as well, and so we can replace this thing, this set, with a group. We can replace this thing with a topological space. We can replace this thing with anything which satisfy the definition of a set. Okay, then G acts on Y if we have a map. Okay, so we have a map from G cross Y to Y, and we denote the images in this way. Okay, so there are many books who will just denote these images in the following way. Okay, so GY or YG, but the advantage of this notation is that it will be easy to remember these two conditions. So what are these two conditions that we must have if it is a group action? This first condition is y raised to power g prime is equal to y raised to power g prime. So this is the same as the power rule that we have per real number, so that's why it's very easy to remember. And the second thing is y raised to power 1 is equal to 1. Once again, it is one of the properties of the real numbers that 2 raised to power 1 is 2, so that's why it's easy to remember in this notation. Okay, and what is this 1? So this 1 is the identity element of this G, and of course in some cases it will be 0, and in some cases it will be matrices. So this 1 really represents the identity of this group G. Okay, so that's how we define group action on a set. Now let's see how we define the group action on a topological space. Then we have this extra condition, that this map from G cross Y to Y has to be a continuous function. Okay, so if we replace Y with a topological space, then we have to introduce an extra thing, that this map G cross Y to Y has to be a continuous function. Now if we have a group G acting on a set Y, and this small y is any element of this capital Y, then the orbit of Y is given by O of Y is equal to y raised to power g, such that G belongs to Y. So what is this y raised to power g? Of course this is the image y gy. Okay, so this image goes to basically some element, okay, y raised to power g. Okay, so basically we are denoting the image of gy by y raised to power g. Okay, so this orbit of Y is basically just take Y and apply all the elements of this group G, and the set that you will get will be of course a subset of Y, and this is called the orbit of Y. Okay, so we shall see some examples of this definition. And the stabilizer of Y is defined as, okay, so once again we are fixing this Y, so it is a set of all elements of the group which fix this Y. Okay, so fix in a sense that when I apply G on Y, then I once again get Y. Okay, so once again this notation y raised to power g is the image of gy to Y. So remember, if we have a group action, then we have a map from G cross Y to Y satisfying certain conditions. So it is this map, and we are denoting the image of gy under this thing by y raised to power g. Okay, so what is stabilizer of an element? Set of all elements of the group which fix this element Y. So fix in a sense that there is no effect on Y by that element of the group G. So set of all elements of the group which make no effect on Y is going to be in the stabilizer of Y. So let's see some examples. So first consider a cyclic group generated by this permutation. Okay, and you can see that 1 goes to 2, 2 goes to 4, 4 goes to 5, 5 goes to 3, and 3 goes to 1. So it's a cycle of length 5. So we can say that it will generate a cyclic group of order 5. Okay. Now consider the action of this group G on the set X. So how we are going to take the action? Okay, so we are going to define the action in the following way. So we need a map from G cross X to X, and I should have the image of each and element of Y corresponding to each and element of the group. Now the point is, it is a cyclic group. So in other words, if I know the image of some element of X under the generator G, then I'll be knowing the image of 1 under each and every element. Okay, so in other words, what do I need to know? I need to know the following images. Okay, so if I know the following images, then I will know the images of each and element of the group, because it is a cyclic group of order 5. So in other words, it will have elements 1, G, G square, G cube, G raised to power 4. Okay, so in this case we are writing down what will happen when this element G, which is the generator of the cyclic group, act on this element 1, 2, 3, 4 and 5. So what will happen when this element G square acts on 1, 2, 3, 4 and 5? So we can easily derive from these 5 expressions that what is going to be G square 1, for example. Okay, so why it is clear? Because we can see the definition of the group action, that y raised to power g prime is equal to y raised to power g prime. So in other words, if I want to see the effect of g square on 1, so in other words I want to see what is going to be 1 raised to power g square, then I should know that this is equal to, according to the definition of the group action, 1 raised to power g raised to power g. So in other words, what is this thing? So this is the effect on 1 by this element g, okay, and then raised to power g. So in other words, the effect by this element g on this element, which is effect of g on 1. Okay, so when this g acts on 1, then we will get some element. So let us come to this definition. So I'm going to define the group action just according to this permutation. So for example, 1 goes to 2, so I'm going to define this as 2. 2 goes to 4, so this is 4. 3 goes to 1, so this is 1. 4 goes to 5, so this is 5. And 5 goes to 3, so this is 3. Okay, now what is going to be the image of g square 1? Okay, because I need to have a map from g cross x to x. So in other words, we are saying that I should have the image corresponding to each and every element of g corresponding to each and every element of x. Okay, so what will be the image of when g square acts on 1? So this is equal to this, and according to definition we should have this. And what is g1? So what happens when g acts on 1? So this is 2. Okay, so this is 2. And what happens when g acts on 2? This is 4. So we can easily see that using these expressions we can get the images of the rest of the elements, and in other words, when rest of the elements of the group G acts on the elements of X, then what will happen? And using this conditions of the group action, we can easily see it. Now let's consider another example where we have a group G which is 1 minus 1. So what is this group? Of course, if it is a group with 2 elements, then it must be isomorphic to C2, cyclic group of order 2. And in this case our set is this real line, and the action is induced by multiplication of real numbers. So in other words, we are saying that how we define the action. So G cross Y to Y. So how it is defined? So take an element of G, take an element of Y, so we are just multiplying these two real numbers. Okay, so g into y. So in particular, if I have 1 and if I have real number 2, then it will go to 2. And similarly, if I have an element -1 and if I have an element 2 from this set y, then this image is -2. So just multiply these two. Okay, so that's what it means by multiplication of real numbers. Okay, so similarly, let's have another instance of this group action. So 100. Okay, so 1 is coming from this group G, and this 100 is coming from real line, which is the set on which we are acting this C2. Okay, so what will happen? Just multiplying these two real numbers, we will get 100. So what will happen when -1 acts on 100? So once again, this is an element of the group and this is an element of the real line, so this is equal to -100. Okay, so in other words, we are saying that if you take an element from this side, so let's call it y, then the image under this element. Okay, so how -1 acts? So when -1 acts, then we will get -y. Okay, so basically if it's on the negative side, then this y will be negative. So negative is inside this y, or just to make things clear, this is -y, so this is +y. Similarly, if I take an element from here, let's call it x, then the image under -x, sorry, an image under this -1 will be -x. Okay, and of course what will happen when 1 acts on these elements, then -y goes to -y, y goes to y, x goes to x, -x goes to -x. So in other words, we are flipping the real line when -1 acts. So we are taking this positive side to the negative side and negative side to the positive side, and we are when we act -1, and when 1 acts, then this is just the identity element. Okay, now let's see what are going to be the orbits and what are going to be the stabilizers of this group action. Okay, so notice that the stabilizer of each and every element which is non-zero is going to be 1. Okay, so in other words, we are asking the following question. So if I denote the element of the group G by this small g, take an element, and what I'm looking for is, so what is Gx? So Gx is basically a set of all elements of the group G such that when we act G on x, then we get x. Okay, so what are the elements? Because in this case x is not equal to 0. Now, is there any element of the group such that when this element of the group acts on G, then we get the same element x? So when -1 act on a non-zero element, then we get the negative multiple of that element. Okay, so it can't be -1, but when one acts on that element, then we get the same element. So in other words, we can say that this is just the identity element. Okay, so this is the stabilizer. So what are going to be the orbits? So as I said earlier, then when we are defining the orbit of an element x, which is a real number and it is non-zero real number, then this is going to be equal to x raised to power g such that g belongs to capital G. So take all the elements of the group and apply them on this x, and that will be your orbit. So in other words, take one element of the G, apply it on the x. Okay, so let's start with 1. Take 1 and apply it on x, and you will get x. Take another element of the group, -1, apply it on x, and you will get -x. And there are only 2 elements in the group, so that's why we have applied all the elements of the group. So this is going to be the orbit of this x. Okay, so that's another example where we have calculated what are going to be the orbits, what are going to be the stabilizers, and what is this group action. Okay, now our next definition is transitive action. So we say that G acts transitively on Y if for each y prime belongs to G, there exists G belongs to capital G such that this happens. So in other words, what I'm trying to say, so if I write down the elements of Y in this way, okay, so this is one element of Y, second element, third element, fourth element, fifth element, sixth element, up to so on. Okay, so there are many other elements as well. Okay, so when we apply some element of the group on some element of y, then we get some other element of y. Okay, so for example, let's apply g on f y5, and let's assume that we get y4. And similarly, if let's apply g prime, some other element of the group, on y2, and let's assume that we get, let's say, y100. Okay, and up to so on. Now this y2, okay, may or may not be connected in this way with y5. Okay, so there may or may not be some element of the group which will take y2 to y5. Okay, so in general this is true, but transitive action, so transitive action says that if this action is transitive, then any two elements are connected. Okay, so take any two elements, y1 and let's say y3, then there will be some element. Okay, so there exists some g belongs to g such that when we apply g on y, then we get g prime. And remember that these y and y prime are any two elements of this okay, so I should say over here the space, the set y. Okay, so take any two elements of the space y, and there exists an element of the group that when we apply that element group of the group on y, then we get y prime. So in other words, there exists another let's call it g2. Okay, so this is connected to this, this is connected to this, this is connected to this. Okay, so if this happens, then we can easily say that there's an element of the group which will take y5 to y100. So what is that element? Okay, so let's call this g3, let's call this g4. Okay, so let's call it g5. So what is that element of the group which will take y5 to y100? Of course, that element is going to be g, g3, g4. Okay, so first apply g, then apply g3, then apply g4, then apply g5, then apply g2, then apply, so let's call it g6, g6, and then let's call it g7, so g7. Okay, so this y5 is connected to y100. Okay, so if this happens, then we say that the group action is transitive. Okay, so each and every element of the set y is connected to each and every other element. Okay, now is this action transitive? So once again, let's call this element to be 1, this element to be 2, 3, 4, 5. Okay, and this is our element g. So this g takes 1 to 2. Okay, so and g takes 2 to 4, and then this g takes 4 to 5, and it takes 5 to 3, and it takes 3 to 1. Okay, so sorry, this is g. Now the question is there an element of the group which takes for example 1 to 4? Of course there is an element, so apply g and then g again. So in other words, when we apply g square on 1, then we will get 4. And similarly, is there an element of the group taking 5 to 2? Of course there is, apply g and then this g and then this g. So apply g cube on 5, so g, 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 and you will get 2. So similarly, we can find an element of the group taking any element of the set x to any other element. So in other words, we can say that the action is transitive. So we also discussed this other action. So let's see if this action is transitive or not. Okay, so we are acting this group C2 on the real line. Now the question is there an element of the group taking 1 to 2? Okay, so let's apply all the elements of the group on 1 and let's see if we will get 2, because if there is some element of the group which will take 1 to 2, then it will be from this set 1 and minus 1. So when we apply 1 on 1, then we will get 1, and when we will apply minus 1 on 1, then we will get minus 1. Okay, so the only elements that this element 1 goes to is 1 and minus 1, so it will never go to 2. Okay, so in other words, there is no element. Okay, so there is no element of G taking 1 to minus 1, so which implies action is not transitive. Okay, so there's another result which says that number of elements in the orbit of G is equal to the number of left cosets of the stabilizer of Y inside the group G. Okay, so we haven't discussed some things that we are using here. So for example, the stabilizer of Y is always going to be a subgroup of G. Okay, and so if it is a subgroup, then we can calculate the number of left cosets. Okay, so a number of elements in the orbit and the stabilizer of Y, they are connected by this important result, and we'll be using this result when we will be exploring the relation between the covering spaces and the fundamental group. So let's begin our discussion, which is going to be our main discussion, and for which we discussed group action. Now if we have a covering space, then for each x belongs to capital X, the inverse image is called the fiber above X. So in other words, what we are saying is, if we have this base space X, okay, and once again I'm going to sketch the covering space as the number of sheets. Okay, so there are some number of sheets above this base space X. So if there exists an element, let's call it X, and this is the projection map P, then the inverse image of X is going to be some collection of elements of the covering space X tilde. Okay, so roughly speaking, we can say that there will be one element in each sheet. Okay, so let's call it X1, and in this sheet there will be another element, let's call it X2, let's call it X3, and up to so on. Okay, so this P inverse X is called the fiber over X. Okay, so this is the fiber over X, and it will be X1, X2, X3, and of course if I take some other element, let's call it A, then P inverse A will be A1, A2, A3. Okay, so remember the example of a covering space of a circle, which is a helix, and we had this projection map P from R1 to S. Now if I have some element over here, okay, so let's call it Y, then the inverse image of Y will be this element. Okay, so sorry, I think it should be somewhere over there. Okay, so let's call it Y1, and then we will have Y2, and up to so on. Okay, so the inverse image of Y is going to be in this case infinite number of elements of R1, and this is going to be a discrete set because this Y1 and Y2 are separated. Okay, so in other words, P inverse of Y in this case is going to be Y1, Y2, up to so on, and this is called fiber over X. Okay, so note that the fundamental group of the base acts on the covering space. Okay, so why this is true? Okay, so once again let's have our base space X, and let's have our covering space X tilde. Okay, so there will be many sheets up to so on. Okay, now if I have an element, okay, so this line says that if pi1 of x is basically fundamental group of the base, then it acts on the covering space. So in other words, I need to have this map. Okay, so what do I need to have? I need to have a function from pi1 cross x tilde to x tilde. So give me an element of the fundamental group and an element of the covering space, I should be able to give you another element of the covering space. Okay, so take an element, let's call it gamma, from the fundamental group. So if it is from the fundamental group, okay, then of course this represents a loop. Okay, now we can say that if it is a path, let's call it f, then I can lift this path to some path inside this covering space x tilde. Okay, so there will be a path inside this covering space. Okay, so let's see. So once again we have sketched these sheets, but this covering space is in fact path connected space, so it can go from this point to this point. Okay, so let's call it f tilde, which is the lifting of this path, which is in fact a loop inside the space x. Okay, so inside this x tilde, which is the covering space, this f tilde doesn't have to be a loop. Okay, so now how this f tilde acts. Okay, so sorry, we have taken this to be f, okay, not gamma. So how this f acts on some element, let's call it x naught tilde of element of x tilde. Okay, so we apply. Okay, so remember we need to give some initial point of this path as well. Okay, so once we give the initial path, then this lifting is unique. Okay, so once you give this initial point, then we can say that we can apply f tilde on x naught, and we will get some other element, let's call it x1. Okay, so x naught tilde, x1 tilde, so this is equal to x1 tilde. Okay, so in particular if this covering space is path connected, then we are sure that this f tilde is not going to be a loop, because there are no loops in the universal cover, because the universal cover is simply connected and the fundamental group is trivial. Okay, so in case x tilde is a universal cover, then we can say that f tilde is not a loop. Okay, so we are sure, and then it will take some element x naught tilde to x1 tilde. Okay, so in particular we can easily see in the example of a circle where we have this thing. So if we have some loop inside the space, so let's say we have a loop taking two circles of this circle. Okay, so the winding number is 2. Okay, so let's call it gamma. Okay, so now when we lift this path, and this is R1 and R1 is simply connected, so when we will lift this thing and we want to take the image of let's say this element which is directly above this element. Okay, so let's call this element to be x naught tilde. Okay, so this loop has winding number 2, so we should have 1 winding and 2 windings. Okay, so this is going to be the image of this. So in other words, when gamma acts on x naught tilde, okay, so then we will get x1 tilde. Okay, so just lift this path to R1 and then take the initial point and follow the path, and the final point will be the image. So that's how we can act fundamental group of the base space on the covering space. So if we have this action, then we have the following result, and we are presenting it without proof. If we have a covering space and x naught is an element of the base space, and y naught be the fiber over x naught. So once again that we have this space x and we have this covering space. Okay, so let's say there is an element x naught, and the inverse image is x1, x2. Okay, so x1 is in this sheet, x2 is in this sheet. Okay, so x1, and then we have x3 up to so on. So these elements x1, x2, x3 are in the fiber over x0. So this result says that the fundamental group of the base space, okay, at point x0 acts transitively on y. So in other words, it will permute all the elements of the fiber. Okay, so it will take 1 to 2, 2 to 3, 3 to 4, or it will take 1 to 100, 100 to 2, and 3 to 97, up to so on. For example, if there are 100 elements in the fiber. Okay, so next statement is, if we have an element in the fiber, then the stabilizer of this element is basically p lower star pi 1 x tilde x naught tilde. Okay, so take the fundamental group of x tilde at that point and push it using this projection map. Okay, so once again let me remind you that this is the image under this functor pi 1 of this continuous function p. Okay, so then push it and then of course you will get a subgroup. Okay, of course we know that if we have okay, so this fundamental group of the covering space, then we will, then if we push it, then we will get a subgroup of the fundamental group of the base space. Okay, so this is going to be the stabilizer of x0. And last but not least, the number of elements in the fiber of x0, which is y, so number of elements in y, okay, is going to be the number of left cosets of this group inside this. Okay, of course we know that when we take the image under p lower star of the fundamental group of the covering space, then it is a subgroup of the fundamental group of the base space. So if it is a subgroup, then we should be able to calculate the number of left cosets. Okay, so that number of left cosets is going to be the number of elements in the fiber over x0. Okay, now we have another result. So it says that if we have a covering space, okay, and if we have two elements x0 and x1 from x, and y0 and y1 be fibers over x0, x1 respectively, then number of elements in the fiber over x0 will be equal to number of elements in the fiber over x1. Okay, so this is once again very easy to see diagrammatically. So once again we have this covering space, we have this base space, we have a projection map, and if we have two elements, let's call it x0 and x1, so in the fiber above x1, so let's call it x0, okay, so let's call it y1, y2, y3, and there will be fiber above x1 as well, let's call it z1, z2, z3. Okay, so p inverse of x0 is equal to y1, y2, y3 up to so on, and p inverse of x1 is going to be equal to z1, z2, z3 up to so on. So this says that if y0 and y1 be fibers, okay, so we have taken this to be y0 and this is y1, then the number of elements in y0 and y1 are always equal. Okay, so once again this is an important result. Now we have this corollary which is very simple consequence of our previous discussion. So it says that the fundamental group of projective space, any real projective space, is going to be Z2. Okay, so how to prove this result? So let's go back to this theorem. We know that the number of elements of the fiber, so they are all equal. Okay, so using this theorem, so they are all equal, and the number of fiber in one particular. Now we have this important corollary of our above discussion. So it says that the fundamental group of real projective space is isomorphic to cyclic group of order 2. So how to prove this result? So before going on with the proof, we know that Pn, so remember this n is greater than or equal to 2. Okay, so this Pn, so let me show this thing for P2R. Okay, so what is P2R? Space of all lines inside R3. Okay, so we have seen this earlier, that I can take a sphere in R3. Okay, and the number of points on S2 represents the point of real projective plane, but then this point and this point represents the same point of the real projective plane. So what we should do is we should take an action of Z2 on S2. So in other words, just identify the opposite points. So if it is x and if it is minus x, then just identify the opposite points of S2 and you will get P2R. Okay, so in other words, if there is a real projective plane, okay, so I'm just going to sketch it as P2R, but in fact it is not really flat. Okay, so it's some curved space, but just for the sake of showing, so each point of P2R will have two inverse images. Okay, so let's call this point to be y, then this y will have two inverse images. So let's call it y1 and y2, and what is the relationship between y1 and y2? That they are related by negative multiple. So y2 is equal to minus y1, for example. Okay, or similarly y1 is equal to minus y2. Okay, so give me an element of P2R, then the inverse images will be 2 points. Okay, so in other words, we can say that, okay, so Sn covers PNR. Okay, or in other words, we can say that Sn is a covering space of this real projective space. Okay, so now we know that we have in fact proved that the fundamental group of Sn is equal to the identity. Okay, now let's go back to our theorem. So it says that the number of elements in the fiber of some element is equal to this number of left cosets of this P lower star pi 1 of the covering space inside this pi 1 x. Okay, and what point or what fiber should we consider? The next theorem answers that the number of elements in each and every fiber are equal. Okay, so we have the following thing, then the number of elements in some fiber. Okay, so let's call it y is going to be equal to pi 1 of PNR. Okay, so the number of left cosets inside this group by this P low star pi 1 of Sn. Now if we have pi 1 Sn to be identity, and we know that this P low star is going to be homomorphism, a group homomorphism. So a group homomorphism takes identity to identity element. So in other words, we can say that this is going to be equal to pi 1 Pn R with identity. And we also know that the number of elements in each and every fiber are going to be 2. Okay, because for example, in this case, take these y1 and y2, so they are going to be in the fiber of y, so there are only 2 elements. Similarly, take any other element and there will be only 2 elements in the fiber. Okay, so we can say that this is equal to 2. So in other words, what we are saying is the order of the group, which is the fundamental group of the real projective space, is going to be equal to 2. Okay, and we know that there is only one group of order 2, and what is that group? It is basically cyclic group of order 2. So basically this result is coming from the classification of the groups. Okay, so if we have a group of order 3, then there is only one group of order 3, which is the cyclic group of order 3. If we have if we have a group of order 4, then it could be C4, it could be C2 cross C2, cross product of cyclic group of order 2. Okay, and similarly, if we have a group of order 5, then there is only one group of order 5, which is C5. Now in this case, we have the order of the group is equal to 2, and there is only one group up to isomorphism, of course, of order 2, and this is C2. So this implies, so by a classification of groups, so by classification of groups, we can say that pi 1 of Pn R, this is isomorphic to Z quotient 2Z. Okay, so that's how we can, for example, compute the fundamental group of real projective planes, and these results that we discussed earlier, which tells us the relation between the covering spaces and the fundamental group. So we can exploit these relations to, for example, explore information about the fundamental group, or to explore the information about the covering spaces. So this is basically, this provides us a bridge between the covering spaces and the fundamental group. Okay, so let's go on with our next result. So this result says that if we have a covering space of X, and X naught is an element of capital X, and Y be fiber over X naught, and if two elements are in the fiber, then their images under P lower star of the fundamental group at those points are conjugate subgroups of pi 1 of X, X naught. So once again, very important result. If we have a covering space, and at 2 points, if we calculate the fundamental group at 2 different points, and of course if there is a continuous map from X tilde to X, then this implies that there is a map between the fundamental groups, okay, pi 1 of X naught tilde to pi 1 of X. Okay, so X naught is the base point, and similarly I will have another map from pi 1 of X tilde X1 tilde to pi 1 of X naught. Okay, and these are subgroups. Okay, so P lower star, so when we apply this thing on pi 1 X tilde X naught tilde, then it is a subgroup of pi 1 X naught, and similarly this P lower star pi 1 of X tilde X1 tilde is a subgroup of pi 1 X naught. So both of these are subgroups of the fundamental group of the base space. Now the question is, what is the relationship between them? So the relationship is that they are conjugate subgroups inside this fundamental group of the base space. Okay, so our next result is, if we have a covering space of the base space X, then a covering transformation is a homeomorphism between X tilde and X tilde. Okay, so let's say this is our covering space, and of course there exists a continuous map P from X tilde to X, and we say that a covering transformation is a homeomorphism from X tilde to X tilde. Okay, so this is a homeomorphism such that when we apply H and then we apply P, then it is the same as applying P. Okay, so in other words, this diagram commutes. Okay, so that's how we define covering transformation. Okay, now of course there can be more than one covering transformations, and we denote the set of all covering transformations by this. Okay, now this theorem is very important. So what is this result? So I'm not going to define the topological definitions that are presented here. So if you are interested, then you can have a look at some book of topology, but we are just going to say that there are some nice conditions on X. Okay, there is some nice space X, so nice means it is connected, locally path connected. So in fact we have discussed these things, connected and locally path connected, in our previous discussions, and we haven't discussed what is semi-locally one connected space, and I would recommend that you can have a look at any book on topology. Okay, so we have a nice space X, okay, and this X tilde P is its universal covering space. So when we say universal covering space, it means it is going to be a covering space, and the fundamental group of this covering space is identity, okay, and it is path connected. Okay, if G is a subgroup of set of all covering transformations, and this group is isomorphic to the fundamental group of the base space. Okay, now this is a very important assumption. We are taking a subgroup of the covering transformations such that that subgroup is isomorphic to the fundamental group of the base space. Okay, then the fundamental group of the quotient space X tilde G, X tilde quotient G, okay, at some point X star, because it is path connected, so just take any point. Okay, so X star is any point of X tilde. So this is going to be isomorphic to G. Okay, so this is an extremely important result where we have collected, we have used this notions of quotient, fundamental group, covering spaces, and many other things. Okay, so for example, if I have a space X which is nice, okay, so nice means there are some topological conditions on X, okay, and we have a universal covering space. So universal covering space means we have a simply connected cover of this nice space, and if we have a group which is isomorphic to the fundamental group, then X tilde quotient G. So when I'm saying X tilde quotient G, so there is a group acting on X tilde, and in this set I'm writing down the orbits of this thing. Okay, so of course we can calculate the orbits, and so this is going to be collection of orbits of the action of G on X tilde. Okay, so why G acts on X tilde? Because G is a subgroup of the covering transformation. So each and every element of this group G can take, so it has the ability to take an element of X tilde to X tilde. Okay, and of course satisfying certain other conditions of the covering transformation. So if we collect these orbits, then this is again going to be a topological space. Okay, so if we have this quotient space, then this quotient space, which is a topological space, has the fundamental group which is isomorphic to G. So once again it is path connected, so in this path connected space we can take any point. Okay, so that is an important result relating fundamental group and universal covers and covering spaces. This is the end of our lecture. Okay, and in fact this is the end of the course as well, because in the next lecture we are going to just review all of the course of algebraic topology. Okay, so in today's lecture we learned what are covering spaces, what are group actions, and the relation between the covering spaces and the fundamental group. Okay, and we also discussed in the last theorem that how to construct a topological space with given fundamental group. Okay, so next time we will review the whole course of algebraic topology. This is the end of the lecture. Thank you very much, and Allah Hafiz.